We can represent the motion of a particle moving along a curve in space using a moving coordinate system. So here we have the tangent vector representing the forward direction of motion, and as we've seen, the normal vector gives the direction in which the path is turning, as we can see. So it's always pointing towards the concave side of the curve at that particular point in the particle's motion. And we'll see that the binormal vector represents the twisting of the motion out of the normal and tangential plane that's created by the normal and tangential vectors. So the binormal vector of a curve is the cross product between the unit tangent vector and the principal unit normal vector, and is thereby perpendicular to both vectors. And therefore these three vectors define a moving right-handed 3D coordinate system or vector frame known as the Frenet frame or the TNB frame. We can represent the acceleration as normal and tangential components to the motion along a curve being a space curve or planar curve, which is more meaningful in representing the motion compared to Cartesian coordinates, which are more convenient for rectilinear motion. So if we start with the velocity vector being the derivative of the position vector with respect to time, and taking a base point along the curve, and the s coordinate being the arc length parameter along the curve, then we can use a chain rule to differentiate r with respect to s and multiply this by ds dt. So recall that the arc length function is a function of the parameter t, and given the speed being the first derivative of the arc length parameter with respect to t is always positive for the motion along a smooth curve, then s is a one-to-one function of t. So dr ds, as we've seen previously, is the unit tangent vector, and that's multiplied by the speed of the particle along the curve. And now we can find the acceleration by differentiating the velocity with respect to time. So here we have the derivative of the unit tangent vector with respect to t by ds dt plus the unit tangent vector by the second derivative of the arc length function with respect to time. So here we apply the product rule of differentiation. So recalling that the principal unit normal vector was the reciprocal of the curvature, but the derivative of the unit tangent vector with respect to s, then we can apply the chain rule to differentiate this vector with respect to s and multiply this by ds dt. So here we have a tangential component of the acceleration being the second derivative of the arc length function with respect to time by the tangential direction or in the direction of the tangent vector plus the component in a normal direction. So we have the first derivative of s with respect to t squared multiplied by dt ds, which is the curvature, and this is the normal component of the acceleration. And furthermore, using this relationship, we can write this term as the first derivative of the magnitude of velocity or speed, and this term can also be written as the speed. So therefore this entire term is the squared magnitude of the velocity. So the acceleration only has tangential and normal components to the motion along the curve. So it's always in a normal and tangential plane, called the osculating plane, which is perpendicular to the binormal vector. So the resultant of the acceleration is the vector sum of the tangential and normal components. So the acceleration is independent of how the object may appear to twist and turn in space. And the tangential component of the acceleration, as we can see, changes the speed of the particle. So it's the rate of change of the speed. And the normal component of the acceleration changes the direction of the particle. And if the speed is constant, then there's no tangential component of the acceleration, as this derivative would be zero. So that's in the case of uniform circular motion, for example. Now we can find the normal component of the acceleration, which is this component, without finding the curvature. So given r will be generally given as a function of t, we can differentiate it twice to find the acceleration and take the squared magnitude of the acceleration vector, which is equal to the square of the tangential component and the square of the normal component. So if we turn this equation around, we can find the magnitude of the acceleration in the normal direction as the square root of the squared magnitude of the acceleration vector minus the square of the tangential component, where the tangential component is this second derivative of the arc length function over here, which is the first derivative of the speed. The torsion, or twisting of motion along a space curve, can be found by taking the rate of change of the binormal vector, being a unit vector, with respect to the arc length parameter along the curve. So recall that the arc length function is taken with respect to some base point, which gives a directed distance from that point. So recall that this vector is orthogonal to the unit tangent vector and the unit normal vector. So it was equal to the cross product between the tangent and normal vectors. And now we can apply the product rule of differentiation. So that gives the cross product between the unit tangent vector and the derivative of the normal vector. And in the next term, we differentiate t with respect to s and take the cross product with the normal vector. Now recall that the normal vector was the reciprocal of the curvature, but the derivative of the unit tangent vector with respect to the arc length parameter. So it's a scalar multiple of dt ds. And therefore the two vectors are parallel, and this cross product evaluates to the zero vector. So that gives dB ds is the cross product between the unit tangent vector and the derivative of the normal vector with respect to s. So therefore this derivative is orthogonal to the unit tangent vector because it results from this cross product, and it's also orthogonal to the binormal vector, because recall that the binormal vector is a unit vector, so it has a constant length throughout the motion, being 1. And therefore, given it's orthogonal to both b and t, it's parallel to the principal unit normal vector. So therefore, dB ds is a scalar multiple of the normal vector. And this is typically taken as negative tau multiplied by n in textbooks. And the scalar tau is called the torsion along the curve. And therefore, given the binormal vector, which is a cross product between the unit tangent and unit normal vectors, then by taking the dot product between dB ds and the normal vector, we obtain minus the torsion constant by the dot product between a unit normal vector and itself. So this here evaluates to 1. Then we can write the torsion function for a smooth curve as minus the derivative of the binormal vector with respect to the arc length parameter dot n hat. And therefore the torsion can be negative, positive or 0, whereas recall the curvature can only be positive. Now we can define 3 planes using these 3 orthogonal vectors. So for example, if we have a particle at some point P, and we have the motion described in terms of these 3 planes that are mutually perpendicular, so it looks something like this. So in this direction, we'd have the unit tangent vector, and in this direction, we have the principal unit normal vector, and the cross product between those results in the binormal vector. And the motion of the particle is along this path, which looks something like this. So this plane over here is called the normal plane, which is defined by the NB vectors. So the curvature being the magnitude of the derivative of the tangent vector with respect to the arc length parameter along the curve is the rate at which this normal plane, defined by the vectors n and b, turns about the binormal vector. As the point P moves along its path. And on the other hand, the torsion tau, which is minus a dot product between a rate of change of the binormal vector along the curve and the normal vector, is the rate at which the osculating plane, which is this plane over here, formed by the tangent and normal vectors, turns about the tangent vector as the point P moves along the curve. So that represents the twisting of the motion. And the BT plane is the other plane called the rectifying plane. Find the acceleration of the motion of a particle along a helix without finding the unit normal and tangent vectors. So recall that the acceleration had a tangential component being the derivative of the speed in the tangent direction plus a normal component being the curvature by the squared magnitude of the velocity or the square of the speed in the normal direction. So differentiating this expression, we have the velocity is minus sine t in the x direction plus cosine t in the y direction plus 2t in the k direction. And therefore the speed, being the magnitude of the velocity, is the square root of sine squared t plus cosine squared t, which is 1, plus 2t squared, which gives 4t squared. So that can also be written as 1 plus 4t squared to the half. And therefore the derivative of the speed with respect to time can be obtained using the chain rule. So as a quick way, we can multiply 8t by a half, and then multiply this by 1 plus 4t squared to the negative a half, which is a square root of 1 plus 4t squared. So this is a tangent component of the acceleration. And now differentiating the velocity, we get the acceleration, which gives minus cosine t in the I direction, minus sine t in the j direction, plus 2 in the k direction. So the acceleration has a magnitude of the square root of cosine squared t plus sine squared t, which is 1, plus 2 squared gives root 5. And therefore the normal component can be obtained as the square root of the squared magnitude of the acceleration, which is 5, minus the square of the tangent component, which gives 16t squared, on 1 plus 4t squared. Find the unit tangent, principal normal and binormal vectors, and the torsion for the following space curve. We'll recall the tangent vector is the velocity function on the magnitude of velocity or speed. So differentiating the position function, we get 3 cosine t in the I direction, minus 3 sine t in the j direction, plus 4 in the k direction. And the magnitude of velocity is 3 squared by cosine squared t plus sine squared t, which is 9, plus 4 squared is 25, and taking the square root gives 5. And the normal vector is the derivative of the tangent vector with respect to t on the magnitude of this vector. So differentiating this, we get minus 3/5 sine t in the I direction, minus 3/5 by cosine t in the j direction, and the k term drops out. And the magnitude of this vector is the square root of 3/5 squared, which is 9 on 25, by sine squared plus cosine squared t, and taking the square root gives a magnitude of 3/5. So if we divide this expression by the magnitude, then the 3/5 cancels. And that's our normal vector. And the binormal vector is the cross product between the unit tangent vector and normal vector. So we have the unit vectors in the first row, and the tangent vector has a component 3/5 cosine t minus 3/5 by sine t and 4/5, and a normal vector has a component minus sine t minus cosine t and 0. So evaluating the determinant, the I component is minus 3/5 sine t by 0 minus 4/5 by cosine t. And the j component is 3/5 cosine t by 0 minus 4/5 by sine t, which gives a positive result, So we have minus 4/5 by sine t. And the k component is 3/5 by cosine t by negative cosine t minus 3/5 by sine t by minus sine t, which gives minus 3/5 in the k direction. And the torsion constant is minus the derivative of the binormal vector with respect to s, and we take the dot product with the normal vector. So using the chain rule, we can obtain dB ds as dB dt by dt ds, which is the reciprocal of the speed. So dB dt is minus 4/5 by sine t in the I direction, minus 4/5 by cosine t in the j direction. And then multiplying this by the reciprocal of the speed, which we previously found to be 5, then we get 25 in the denominator. And if you take the dot product with the normal vector, we get 4 on 25 by sine squared t plus 4 on 25 by cosine squared t, which is positive 4 on 25, and therefore we have minus 4 on 25, which is the torsion of the space curve. Find the equations for the normal, osculating, and rectifying planes at t equals pi on 2. So we can draw the following schematic, where we have the motion of a point along a curve, and the tangent vector in one direction, and a normal vector is orthogonal to this vector, and the binormal vector is orthogonal to both vectors. So that gives 3 planes, where this plane, formed by the normal and binormal vectors, is the normal plane, and this plane, formed by the tangent and normal vector, is the osculating plane, and this plane here is the rectifying plane. So to define these 3 planes, we just need this point and a normal to each plane. So the point P is R at pi on 2. So cosine pi on 2 is 0, sine pi on 2 is 1, and the k component is pi on 2. So they're the coordinates of our point, which is on all 3 planes. So we have 0, 1, and pi on 2. And the tangent vector, which is normal to the normal plane, is the velocity on the magnitude of the velocity. So differentiating r, we get minus sine t in the I direction, plus cosine t in the j direction, plus 1 in the k direction. So therefore the magnitude of this velocity vector is the square root of sine squared t plus cosine squared t, which is 1, plus 1 squared is 2. So the magnitude of this vector is root 2. And the normal vector is obtained by differentiating this vector. So I have the derivative of the tangent vector with respect to t on the magnitude of this derivative. So we get minus cosine t in the I direction, minus sine t in the j direction, and 0 in the k direction. And the magnitude of this vector is the square root of cosine squared t plus sine squared t, which is 1. And the binormal vector is the cross product between a tangent and normal vector. So we have I, j, and k. And the components of the unit tangent vector in the second row. So we have cosine t on root 2 and 1 on root 2. And the components of the normal vector in the third row, which are minus cosine t and minus sine t and 0. So the ith component is cosine t on root 2 by 0 minus 1 on root 2 by minus sine t, which gives sine t on root 2 in the I direction. And the jth component is this term by 0 minus 1 on root 2 by minus cosine t, which is positive, and therefore we subtract cosine t on root 2 in the j direction. And the k component is this term by this term, which is sine squared t on root 2 minus cosine squared t on root 2. So we have plus 1 on root 2 in the k direction. And recall the equation of a plane is the dot product between a normal vector to the plane with a vector on the plane defined from 2 points. So we have PQ in this case. And these vectors are orthogonal. Let's make a bit of space over here. And for the normal plane, the normal vector to this plane is the tangent unit vector. So we have the first component being minus sine t on root 2 by x minus x naught plus cosine t on root 2 by y minus y naught plus 1 on root 2 by z minus z naught. And that's equal to 0. And you can simplify this, which gives the equation of the normal plane. Now let's make a bit of space here. And for the osculating plane, the normal vector to this plane is the binormal vector. So we have sine t on root 2 by the coordinate x of this point on the plane minus the x coordinate of point P, which is 0. And then we have minus cosine t on root 2 by the y coordinate minus 1 and plus 1 on root 2 by z minus pi on 2, which is equal to 0. And let's make a bit of space over here. So this here is for the osculating plane. And the rectifying plane has a normal, being the principal unit normal vector. So we have minus cosine t by x minus 0 minus sine t by y minus 1, and the z component is 0. So that's for the rectifying plane. And you can substitute t equals pi on 2 to get the final equations for these planes.